All right, we are going to focus quite a bit here at the start of this class on simulation. We're finally going to get back to simulation a bit. So we're going to simulate random variables, normal, binomial, and Poisson random variables. That's going to take a good chunk of Lecture A. Lecture A, I hope, will also include talking more about confidence intervals, to estimate population means, when the population standard deviation is known, though that's an unrealistic assumption, but we still assume it anyway to keep things as simple as possible. Lecture B will do more on confidence intervals, I'm sure, and we will introduce the idea of hypothesis testing, which is probably the most difficult conceptual thing for the semester, but also one of the most important. I do want to start off by doing some Mathematica demos. The Mathematica code, again, is something you don't need to know. I was having fun with it this morning, actually. That's one of the things I do to have fun, is I play with Mathematica code to do various things that I want to do. I hope what I show you, you will think is kind of neat. I do ordinary things for fun, too, so it's not just doing math. So we're going to sample from normal distributions, binomial, Poisson, and I even had one more thing that was sort of a little extra fun for me, and that's to simulate, to model some football, a user-defined distribution, and my example is Adrian Peterson's rushing stats from his MVP 2012 season, so we'll see if I can model that.
Quick question about this.
Yeah.
When you watch football, do you think like statistical, like how many yards like each carry is, or do you like?
I do sometimes, yeah. I mean, I enjoy the game too.
Does your wife watch it with you? Does she like be like, shut up?
No, I don't usually say those kinds of things. I'm usually just thinking. Maybe once in a long while.
The funny thing is, since I've been in this side, I've actually did that like 4 times. Just like, I wonder what's the standard deviation of his carries.
Cool. You're thinking statistically.
Unfortunately, yeah.
And you're well dressed. You're well dressed today. Do you want to show your mom what you're wearing?
Mom, she might not like it.
Do you count cards at casinos?
Do I count cars at casinos?
This is Bethel.
Count cards.
Bethel.
Yeah, I don't go to casinos.
Bethel, on school.
Okay, so this one I've actually, I think, shown you one like this before. It's just a graph of a normal distribution. This is the standard normal distribution, by the way, to start with. And by the way, the graph actually is above the x-axis forever. In both directions, it never touches the x-axis. It's called a horizontal asymptote. Actually, graphs can touch horizontal asymptotes, but this one doesn't. But it sort of approaches the x-axis fast enough that the total area underneath it is equal to 1. And the inflection points are at 1 and -1. That's one standard deviation away from the mean. Go up to this graph. This is where the graph changes from concave down to concave up, right at that point and right above that point right there. Anyway, a little fun with this. You can change the mean. That just shifts the graph horizontally. You can change the standard deviation. That changes the spread. It does change the height too, because the area always has to stay 1 no matter what. I think I've shown that to you before. So, this morning I was doing something different in that I was also generating data, simulated data from a normal distribution with a command called RANDBETWEEN. You don't need to worry about what that means, but here is some data that I generate for different sample sizes. K is the sample size here. Okay, that's standard normal data. I'm pretending that this has been generated by doing some actual experiments where you gather data about a random, standard normal random variable. You can see about equally many positives as negatives, and they are all mostly between -2 and +2. Are any less than -2 or bigger than +2? Well, that one is. About 5% of the time, they should be either bigger than 2 or less than -2 because of the 68, 95, 99.7 rule. Any others? I don't see any others offhand. Though if I go back and redo this, I get different data. And there is one that's bigger than 2. Any less than -2? Maybe, but I don't see any right at the moment. I can also change the mean and the standard deviation. Now I made the mean a lot bigger, and those numbers are all now positive. I can make the standard deviation bigger. Now, even though the numbers are generally bigger, I do get some negatives. Okay? So that's simulated data, the raw data itself. I can make a graph of such a thing. The values of the data as a time series. Thinking of each number that I go on as another trial, another sample essentially, and calculating the value of the data point. It's very random. That's what you should expect when you're doing random sampling. I can once again change the mean and all the values go up or down, and I can change the standard deviation and I change the spread. So that was kind of fun too. I made a histogram as well that models the simulated data and compares it also to the theoretical distribution. So you've got the theoretical distribution, that's the curve that you see, and the histogram, that's a histogram for data. Okay, and you can see that the theoretical distribution is a good model. I can do something similar with binomials. Here's a binomial plot. N is the number of trials. I started with 10 here. P is the probability of success. This is 0.5, and you can see that N is 10 and P is 0.5. I put a normal curve over there that accurately reflects the basic idea of the distribution. I can change the value of N. I can change the probability of success. It's not always well modeled by a normal, because that's a very left-skewed distribution now when P is high. The normal curve's doing okay when you're close to high values, but not so well for low values. And by the way, I'm not sure why it's making these disks down here and just dots in here. I'm not sure why this is not graphing as well as you might hope. So binomials are not always symmetric. Sometimes they can be very skewed. When P is very small, the probability of success is small. It's a right skew. When P is large, close to 1, it's a left distribution. And the normal curve doesn't work as well as you might hope in that case. Once again, I can model gathering data. Here's data about a binomial random variable with n equals 10 and p equals 0.5. So if you had a baseball player who was a super great hitter, 500 hitter, and they got up to bat 10 times, this would be a simulation of the number of hits they would get in 10 at-bats. More typically, P would be lower, and so you would expect smaller numbers. And that's what those are now, smaller numbers. There's your typical baseball player, actually. Probability of success of 0.268, 268 batting average if they get 10 at-bats. This might be a typical run of how many hits they got in 10 at-bats. If I go down to 5 at-bats, that's more like a game. There's a run of a certain number of hits in 5 at-bats for a typical baseball player. And you could, for example, count how many games where they went over by counting the number of zeros. You can make a graph like this one. Random scatter again. And I can make a histogram and show how the binomial distribution models it. The scale, the vertical scale here is not right. Actually, I'm a little confused by this because it looked right on my computer, so I'm not sure what I did wrong to make the vertical scale off on that one. I did the same kind of thing for Poisson. I think I won't take the time to show you that since we're running low on time for this anyway. So we'll go to Adrian Peterson's 2012 season. Uh-oh. This is not going to work, I think, because, let's see, maybe it will. Oh yeah, I did this on my computer. And now I'm not on my computer. Let's see, let me try something else here. I think I need to try picking this off of this computer if it'll let me. Oh. Okay, I did this on my computer ahead of time. And so it's not going to work now because it's not on my computer. I suppose I could try looking at this particular file on this computer. Let's see here. This is the file that I want. Copy and paste that, maybe that'll work. Let's see if that works. No, not found. I need the file path here, and I don't want to take the time to try to find it. Okay, let me do a file picker on my computer. Sorry about that. We're going to have to save Adrian Peterson's simulation for next time. Okay? It was really cool. I got to model simulated games. I'll show it to you more next time, and I'll try to give you an indication of how a football coach might use it. Might use the simulation. I'll do that next time. All right. What kind of simulations should you be able to do? Well, obviously not Mathematica, because you don't know Mathematica. So what instead? We know spreadsheets. Here's what I'm going to want you to do for next time. We'll do a different simulation next class that'll be due for the class after that, okay? Here's what I'm going to want you to do. For this particular simulation, we're going to model an entire 1977 season over and over and over again for Rod Carew when he had his great batting average of .388. The probability of success was .388. I remember, because this was the first time I liked baseball, and I kept track of his statistics, that he had 616 at-bats that season. He had 239 hits in 616 at-bats. I remember that he had 38 doubles, 16 triples, 14 home runs, 100 runs batted in, and 128 runs scored, and I think 23 stolen bases. So yeah, he was an MVP. He was very good that season. So what we're going to do is we're going to simulate his 1977 season over and over again. Look at the at-bats over there. There's 616 at-bats. We're going to simulate his season like this. We're going to think of a hit as success and a failure to get hit as failure. I think we can do this all at once. We're going to do equals COUNTIF. Okay? COUNTIF. What are we going to count? Let's see. That's not what I want, actually. I just want a plain if. Okay? What am I going to do here? I'm going to generate a bunch of S's and F's, successes and failures, hits and non-hits. I'll put S's and F's. I'm going to want to come up S, success, about 38.8% of the time. And I'm going to want to come up failure about 1 minus 0.388, 0.612, 61.2% of the time. How could I do that? I could use RANDBETWEEN 1, 1,000. Remember, RANDBETWEEN generates random whole numbers between the starting number and the ending number. So I could use equals RANDBETWEEN from 1 to 1,000. If that thing is less than or equal to 388, what value do I return? If that's true, I return an S for success. Else, what else do I return if it's false? I return an F for failure. I think I need to put them in quotes. Emphasizing this text. So what's this going to do? Okay, let me remind you what it's going to do. So RANDBETWEEN is going to generate a random whole number between 1 and 1,000. The first 388 of those I'm thinking of as being a hit, success, because its average is 0.388. The rest, the other 612 of them, I'm going to think of as failure. And so by doing this, it's going to return an S if this is true, and an F if it's not true. So it should be an S about 38.8% of the time. The first one's an S. Is the second one? Well, when I copy and paste, it changes anyway. The first one might change. I get some S's and some F's. Maybe the first game he went 1 for 4. Maybe the second game he gets 4 at-bats, he goes 1 for 4. Okay, this one stayed 1 for 4. 1 S and 2 and 3 F's. How about the third game? There he's 3 for 4. 3 S's and 1 F. These changed. This one was 3 for 4 now, and this one's 4 for 4. Wow, how about that? He had a good first 3 games there if he got 4 at-bats in every game. Do this over and over again. 616 times. Waiting, 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 waiting. It's easy to shoot too far and then you come back the other way and you miss it. So don't go too fast here. Start to slow. slow down as we approach 616. Okay, there's a simulated 1977 season. Remember I said he got 239 hits and 616 at bats. Let's see, this goes down to row 619. Looking over here, 619. Let's do equals COUNTIF right here. COUNTIF C4 through C619. Count it if it's equal to S. Before when I used COUNTIFs, I've been counting cumulative things, so this is a little different use of COUNTIF. I'm going to look through the S's and F's, and I'm going to count how many of them are S's. And actually, with what's in there right now, it's 234 of them. Almost 239. If I enter it, will it be 234? I'm not sure if it's going to change or not. It changed. 238. Remember I said he had 239 hits and 616 at-bats in 1977. That's what actually happened. So in the simulated season, something slightly different happened, but close. And his batting average would then be 238 divided by 616. In that simulated season, it was a little less than 388. Here's a new simulated season. He got 247 hits and 616 at-bats, and his batting average was over 400, which is incredible. That didn't happen, but it could have happened if he really was that good that season, which he was. Okay, it could have happened by chance that he would have gotten a batting average 400, over 400, which is pretty amazing. So I'm going to want you to do this over and over again in these simulation columns. Going over to column Z, so that's going to be, starting in column F, that's going to be 20 times. There's going to be 20 simulated seasons. And ultimately, I'm going to want you to compute his batting average in each season and see if any of them come out higher than 400. So how can you do this here? Take this stuff, copy and paste this entire column of the S's and F's that have the equals ifs in them. Whoa, went too far. Copy and paste that over into these columns, column F through column Z, copy, paste. We've now got 20 simulated seasons. Go down to the bottom, and in each one let's calculate his batting average. This is actually pretty similar to some things we've done before. The batting average is really like a sample proportion, a p-hat, for these 20 different seasons. We've done this before. This is not that much different than what we've done before. You can use equals COUNTIF. These things started in what? Was it row 3 or row, I forgot. Row 4, I think? Row 4. They start in row 4. COUNTIF. This first one is F4 through F619. In quotes, put equals S. Can you see that? I know it's kind of small. For this one, for column F, it's 238 only, again, close to 239. Also divide this by 16. You might as well do that right away. 616. The number of bats. Do that right away. And now do it for each of these columns. Copy and paste this over through column Z. There we go. There was a bunch of 1977 simulated seasons. And how many of them did he hit over 400? This one, the second one right there, a third, fourth. Wow, 440. Unbelievable. That would have been a world record. Fifth, sixth. 6 out of 20 for my simulation of those seasons did he hit over 400. 30% of them. Wow. So he definitely had a decent chance of getting 400 that season when he was batting that well. That's sort of thinking about his population batting average being 388. Now, was that really his population batting average? Not if you consider his whole career. It's just for that season. So, I mean, you might be thinking to yourself, well, shouldn't we think about his whole career instead of just that season? Probably, but we're just pretending, okay? We're simulating based on that season. Got the idea here? I showed you what to do. You can watch the video. As I've noticed, people do watch videos more when I do the Excel simulations for your electronic. Okay. We're going to do a different simulation, more of a game-by-game thing next time, please. And I will try to get the Adrian Peterson one to work.
Do you think you can send that out in an email to Adrian Peterson?
Yeah, I could send you at least a picture of the graph that I got. Okay, so simulation brings probability to life, okay? It makes it seem more real, I think. Makes you see that, you know, how to interpret it in repeated sampling. Any one time you do a sample, it's your assessment of the chances, which maybe you might think of as affecting your betting odds if you were betting. But in reality, you want to think of it in terms of repeated sampling over and over again. All right, let's review binomial random variables focused on what's the binomial setting and also what's the Poisson setting. These ideas could be on today's quiz as far as future quizzes. How do you identify whether a binomial is random, whether a random variable is binomial or Poisson, for example? What is a binomial setting? This is a review. The key difference between a binomial and a Poisson at the most basic level is that with a binomial you have a fixed number of trials, n. So that's an upper limit on how big x can be, the count. You're counting successes still, but it can't be bigger than n because that's the number of trials. Like at number of at-bats or number of free throw attempts, you've got a fixed upper limit on what n can be. Whereas with Poisson, there is no fixed upper limit on how big x is. The count of successes could theoretically be arbitrarily high. Though in practice, it's not usually arbitrarily very high. You're counting successes. You assume the probability of success on each trial is constant, p, and it's independent of what happened on other outcomes, on other trials that came before. X again counts the number of successes. Since n is the number of trials, x can take on any value, 0, 1, 2, 3, 4, etc. up through n. That's a binomial setting. Many times when people do try to apply binomial random variables, they definitely have an n, and they definitely count the number of successes. What might be more dubious is the independence assumption and the constant probability of success assumption. For baseball players, for example, maybe there's the psychology of what happened in their previous at-bat. They struck out and they felt real embarrassed. Or maybe they're facing a tougher pitcher this at-bat. So those kinds of assumptions are a little less valid because of that. Though over the long run, on average, you might say, binomial might be a very good model anyway. What's a Poisson setting? Now you want to count the number of times x occurs in some specified continuous interval of time, for example, or interval of distance, or an area, or a volume. You might want to count how many, I don't know, mosquitoes are in 1 square acre of land down near people level, so they're biting. Okay, they can bite. That would be a certain area of land, and you're trying to estimate the distribution, how many mosquitoes to expect anytime you perform the experiment. So it's got to be a consistent time of day probably, and a consistent time of the year like the summer, to try to apply a Poisson distribution for that kind of count. But Poisson definitely makes more sense than binomial, because the number of mosquitoes could be, you know, how big? Arbitrarily big as far as you know. You don't have a clear upper limit. We focused on the earthquake example. What is a Poisson setting itself? It's a little bit more technical. You don't really need to know the details here, except maybe at a real intuitive level. To technically be a Poisson setting, the number of successes that occur in any unit of measure, like the unit of time, like 1 hour or 1 day or 1 year, or length, like a foot or a meter, or a kilometer or a mile, or area, like an acre, or a square mile or a square kilometer, or a volume, like a liter. The number of successes that you count is independent of the number of successes that occur in any non-overlapping unit of measure. Like if I was trying to count the number of bacteria on this ruler here, that's 1 meter long, okay? And I had another ruler that was also 1 meter long right next to it. The number of bacteria on this one should be independent of the number of bacteria on that one. Now that's kind of a dubious assumption because there's maybe the similar kind of rulers, same kind of wood in a similar environment, but maybe it's somewhat reasonable to assume. The probability of success will occur in a unit of measure is the same for all units of equal size, like 1 meter, and it's proportional to the size of the unit. If I had 2 meters, I might expect twice as many bacteria. Now with bacteria, you're talking about billions of them, so it's probably better to use a normal distribution or something anyway. But it certainly makes some sense that the number of bacteria that you would count would be proportional to the size of the unit. And the probability of 2 more successes will occur in a unit approaches 0 as the size of the unit becomes smaller. So bacteria, you'd have to be pretty small. You know, like you'd have to imagine a ruler shrinking down to microscopic size, less than 1 micron across or something, and then you wouldn't expect any bacteria on a ruler that small, for example. That's kind of a silly example, but just the basic idea. With mosquitoes, you're talking about a really tiny unit of area. You're standing over, maybe there's hardly any mosquitoes, 1 or 2 in that small unit of area. Those are not the best examples. They just came to my mind right off the top of my head there. Okay, so for the quiz and future quizzes and homework too, you should be able to identify Poisson and binomial settings. You should be able to use the formulas as we have as well. And you should know how to use the spreadsheet. For the assignment due next week, next Tuesday, you'll be doing more problems on binomials and Poissons, but this time you'll be using the spreadsheet. You'll be using, you've done that to some extent already, but you'll be using more, the built-in formulas. All right, with the remaining time here in Lecture A, let's talk more about the confidence intervals, which you should know for the test as well. I'm going to jump right ahead to the general formula. This is a slide I did not show you last time, because I do want you to know the general formula for the quiz and for future quizzes. Okay, first of all, the setting. You have to realize what the point is. You're trying to estimate a population parameter, in this case a population mean, mu. Okay? That's your overarching goal. You've got some population that's got some mean of some trait, like the mean weight of everybody in the country, or the mean height, or the mean time they watch TV, or watch YouTube, or browse the internet in general. Some unknown population parameter, unknown and perhaps unknowable. Nobody could know it, except God. What's the mean TV watching time per day for everybody in the whole country? Even if you surveyed people, everybody, you'd still be estimating. It's unknown and unknowable, but you'd still like to estimate. People do this kind of thing all the time. X bar, or sample mean, is your 1 point estimate. One number that can estimate mu. But because it's just one number, it's not likely to be exactly right. In fact, it's probably, almost definitely with 100% probability, not right exactly. But that's not really the point, you just hope it's close. And the margin of error, taking your point estimate and expanding it to an interval estimate, gives you some cushion, gives you an interval of numbers along a number line that you feel pretty confident, hopefully, contains the truth. Somewhere between the left endpoint and the right endpoint is the truth. You want to know that's true, and you want to be able to assess how confident that you are. The letter C in this chapter is the letter that represents the confidence level. The most common C to use is 95%. or 0.95 is a decimal. But it's not set in stone. You don't have to use a 95% interval. You could use a 99% interval if you want to be more confident, or a 90% interval if you want to be less confident. Now you might wonder, well, why would you want to be less confident? Wouldn't you want to be more confident? Well, yes, but there are always trade-offs. If you want a bigger level of confidence, 99% for example, that means the interval's got to be bigger, which might be less useful because, you know, it's a wider range of possibilities. Bigger intervals are less useful. You're more confident in them, but they're less useful. At the extreme, the entire Riemann line could be thought of as a 100% confident interval, but that's not useful at all because it doesn't pin down the value of mu at all. It could be anything. So there's always this game going on between I want high confidence, but I want a small interval. Can you have the best of both worlds? Yes, but that's also with a caveat. You can have the best of both worlds if you up your sample size. But the caveat for that is that it takes more time and money. So there's always trade-offs in using these ideas in practice. I will review those things as we go. The general formula looks like this. It's an estimate plus or minus mo. What's mo? Margin of error. Mo stands for margin of error, which our book typically just writes as an M, and that's fine. You can just use an M. EST stands for estimate. X bar is our point estimate for mu. There's the formula. You used this a little bit last time. For a 95% confidence interval, you used it on your homework. You remember what the Z star was for your assignment for today? 1.96. If you want 95% confidence in this kind of situation where you're trying to estimate mu, and you happen to know sigma, which again is unrealistic, but we're pretending that we do, then Z star is 1.96, close to 2. Initially we use 2. More accurately, if you want a little bit more accuracy, especially if this number is big, we use Z star equals 1.96. What's the star? It's not a power. It's just an indicator saying this is a special number. Z star is a special number. Again, it's 1.96 for 95% confidence. For other levels of confidence, it's different. Okay, let's take the quiz.